Right, now when we started out this discussion of eigenvectors and eigenvalues, we made a comparison between multiplying a matrix times a vector with multiplying a number times a vector. So we're kind of comparing matrix multiplication to ordinary multiplication. In this section, we're going to drive that a little bit farther. And you know that, of course, in ordinary algebra, you can take polynomials, or you can take squares and cubes and so on. And we can do the same thing with matrices. If you have a polynomial, for instance, in the unknown x, okay, we know what this means. That for any number x, we could plug x in and get a number output. For instance, if I plugged in x equals 0, I would get 14. If I plugged in x equals minus 1, I would get 14 minus 9, that's minus 5, minus 3, minus 8, and then this would be plus 7, gives minus 1, and then you get plus, you would get 0. So we know how to plug numbers into polynomials, but in fact we could plug matrices into polynomials as well. There's no reason why we can't, because we can multiply matrices by each other. So how would you do this? Well, first of all, notice that 14 is like 14 times x to the 0 power, because any number to the 0 power is 1. So this is like the coefficient of the 0 power, right? Now we're going to call the 0 power of any matrix, we're going to call that the identity, because x to the 0 is 1. It makes sense that if d to the 0 should be the identity, so we'll just be making that identification. All right, so if I have a matrix D, I have d to the 0, I'm calling that the identity, and then I have d, and then d squared is just d times d, d cubed is d times d times d, which I can compute as d times d squared, and d to the 4th is d times d cubed. You can do these matrix multiplications with Sage and verify that they're correct. And to form the polynomial of this matrix D, I simply plug these matrices in to these entries here. This actually should be 14 times d to the 0, or 14 times I. A little misprint there. All right. So if we plug I in, 14i in there, 19d, this is d here, this is d squared, this is d cubed, this is d to the 4th. Okay, and we know how to add matrices. We add them entry by entry. So in fact, we have this result for our polynomial evaluated at the matrix D. Okay, so far that just seems like a mathematical exercise. We'll go a little farther. Now notice that this polynomial p of x, if we're just considering the ordinary polynomial, it factors in this way. Now the point is that this is a polynomial identity. This polynomial can be factored in this way. And if we plug any number x in, then and evaluate the left-hand side, we'll get the same result as the right-hand side. Notice that the right-hand side is a little bit easier to evaluate than the left-hand side. For instance, if x equals 2, on the right-hand side, I can tell automatically that the result is 0. Remember, I tried before x equal minus 1 and I got 0. On the right-hand side, I see that automatically. On the left-hand side, that's difficult to see. All right, so this is a polynomial identity. In fact, we can not just do this with numbers for x, but matrices for x as well. If I plug d in for x, then I can plug d in on both sides and still get a true equation. Okay, so now this right-hand side is a little bit easier to compute. Now for d minus 2, I interpret that as d minus 2 times the identity matrix. Okay, and for d minus 7, that's d minus 7 times the identity matrix. Okay, so the point is, I'm taking this ordinary polynomial identity and doing the same thing with matrices, just so long as instead of these constant terms, you interpret that as the constant times the identity matrix. So here it is. Here's this polynomial expression with the matrix D substituted in. And then you can go ahead and compute this, d minus 2i3. How do you compute that? Well, D was this matrix here. If I was going to take d minus 2i3, well, the diagonal entries I have to subtract 2 from. So I'm going to get minus 3, minus 2, minus 1 on the diagonal. And all the off diagonals are the same. So I'm going to get 3, 2, minus 2, 1, minus 3, 1. So that's how I would compute d minus 2i3. If I needed to compute d minus 7i3, I do the same thing, except instead of subtracting 2 from every diagonal entry, I subtract a 7. Okay, so if I do this, you can see that here the diagonal entries were minus 3, minus 2, minus 1. And here when we do the evaluation, we get d minus 2i3. This is evaluated d minus 7i3, d plus i3 squared. If you multiply these 4 matrices together, you get the very same result. Okay, so far this is just a convenience, but we're going to use this fact to great advantage later on. All right, so I'm going to stop here and have this brief video, and then we'll go on from there.